Good morning everyone. Myself Sandhiri Swetha. I'm working as assistant professor in ECE department, St. Peter's Engineering College. Today I'm going to give a lecture in the subject electronic circuit analysis, and the topic is multivibrators. So today's topic is multivibrators. So firstly, multi means many. Vibrator means oscillator. So what is multivibrator is a circuit which can give many oscillations. A circuit which can give many oscillations is a multivibrator. This circuit we will be constructing with active elements like BJT, FET and operational amplifier. Here I am using the active element as bipolar junction transistor. So multivibrator is a regenerative circuit which uses two active elements, that is two transistors I am taking. One transistor I named it as Q1 and other transistor I named it as Q2, which are connected in this manner. The output of first transistor is connected back to input of second transistor through some coupling element, and the output of second transistor is connected back to first transistor input through some coupling element. This type of connection is called as cross coupled connection. In all the multivibrators we use cross coupled connection. The cross coupled connection means output of first transistor is connected back to the input of the second transistor through some coupling element, and the output of second transistor is connected back to the input of the first transistor through the coupling element. So here, based on these two coupling elements, our multivibrators are classified into different types. So here the coupling elements can be resistors and capacitors. Two coupling elements we can use. So if both the coupling elements are resistors, then this coupling element is a resistor, this coupling element is a resistor, then the multivibrator is bistable multivibrator. So in bistable multivibrator, both the coupling elements we are using are the resistors. DC coupling we will use. And the second case is one coupling element is resistor and other coupling element is capacitor. So here I am using resistor and here I am using capacitor. So one coupling element is resistor and other coupling element is capacitor. Then we get another multivibrator which is monostable multivibrator. And the third one is both the coupling elements are capacitors only. Both the coupling elements are capacitors. So if both the coupling elements are capacitors, then that type of coupling is AC coupling. So the multivibrator which uses both the coupling elements are capacitors is Astable multivibrator. So based on these coupling elements, our multivibrators are classified into three different types: bistable multivibrator, monostable multivibrator and astable multivibrator. In bistable multivibrator, both the coupling elements we are using are resistors. In monostable multivibrator, one coupling element is capacitor and other coupling element is resistor. And in astable multivibrator, both the coupling elements we are using are capacitors. So in this way our multivibrators are classified: bistable, monostable and astable. So other than this, based on coupling multivibrators classification, we can also classify it based on states. So each of this multivibrator is having two states. So bistable multivibrator is having two states, monostable multivibrator is having two states, and astable multivibrator is also having two states. So in bistable multivibrator, as the term bi means two. So two stable states. Bi means two and the two states are stable states. So in bistable multivibrator, two states are stable states. both the states are stable states. And as both the states are stable states, in bistable multivibrator, there is no quasi-stable state. In monostable multivibrator, as the term mono means one. So one stable state, one is stable state, and one is quasi-stable state. Coming to astable multivibrator, it is also having two states. In astable multivibrator, the two states are quasi-stable states only. So in bistable multivibrator, bi means two stable states. So here the two states are stable states and there is no quasi-stable state. Coming to monostable multivibrator, mono means one. So here one is stable state and the other is quasi-stable state. And coming to astable multivibrator, here also two states are there. Out of the two states, both are quasi-stable states only. So overall we can say in bistable, so if you can just give a comparison, stable state, quasi state. So in bistable we have two stable states, zero quasi stable states. Coming to monostable multivibrator, one is stable state, one is quasi state. And coming to astable multivibrator, zero stable states, two quasi stable states. So here we need to know what is stable state and what is quasi stable state. Stable state and quasi-stable state. So here if we can understand what is stable state and what is quasi-stable state, it will be easy to understand the classification of multivibrators very clearly. So stable state is also called as permanent state. Stable state is also called as permanent state. And coming to quasi-stable state, it is called as temporary state. Stable state is also called as permanent state. Permanent state, as the name it says, it is having it is permanently in a particular state. So if at all we want to change the state, we need to apply external triggering, then only the multivibrator comes out of the state, because it is a stable state or permanent state. As the name it says, it will be in continuously in a one particular state until we apply a triggering. So if we apply a triggering, it comes out of the state. Suppose if the multivibrator is at this level. So in order to change the state from here to here, we need to apply some external triggering, then only it will change the state from one state to another state. So that type of state is called as a stable state or permanent state. Coming to quasi-stable state, quasi-stable state is also called as temporary state. Let me assume my multivibrator is in particular this level. So without applying any external triggering, it automatically changes the state. Without applying any external triggering, it comes out of this level and goes to this level. So without need of any external triggering, automatically quasi-stable state comes out of it after particular duration of time. So in stable state, we need to apply external triggering to change state from one level to the another level, And coming to quasi-stable state or temporary state, without applying any external triggering, after a predefined time, it automatically changes from one level to the another level. So the definition of stable state is, it is also called as permanent state. The multivibrator is continuously in that level. When external triggering is applied, it comes out of the state. Coming to quasi-stable state, it is also called as temporary state. We need not to apply any external triggering. Automatically, after some duration of time, it comes out of the state. So this is the definition of stable state, and this is the definition of quasi-stable state. So we'll come back to multivibrators classification once. So here in bistable multivibrator, we have two stable states. So both the states are stable state. Now we can define like how many number of triggerings are required. Number of triggerings. So here in bistable multivibrator, both the states are stable state. As just now we discussed, a stable state requires a triggering. Without a triggering, it will not come out of the state. So here I have two stable states. I require two number of triggerings. Coming to monostable multivibrator, it has one stable state, one quasi-stable state. Whenever your multivibrator is in stable state, we need a triggering. Whenever your multivibrator is in quasi-stable state, we need not to apply any external triggering. So total monostable multivibrator, we need one external trigger to change the state from stable to quasi. And coming to astable multivibrator, it has zero stable state, and the both states are quasi-stable states or temporary stable states. So as we don't have any stable states here, we need not to apply any external trigger, because both are quasi-states, both are temporary states. It automatically changes the state. So the number of triggerings required are 0. This is the basic classification of multivibrators in regard with number of stable states, number of quasi-stable states, and the number of triggerings required. And we can also write here bistable multivibrator. Different names are bistable multivibrator is also called as flip-flop. It is also called as binary. It is also called as Eccles-Jordan method. Monostable multivibrator is also called as one-shot. Why it is called one-shot? Because it generates one pulse. One stable state it has, it generates one pulse. It is also called as one-shot, or it is also called as pulse generator, because it generates only single pulse. Coming to astable multivibrator, as we don't have any stable state, continuously the output is changing from one state to another state, that is quasi states, without applying any triggering. It generates square wave, continuous oscillations of square wave. Means your output is like this in astable multivibrator. So as we are not applying any triggering, so astable multivibrator is named as free running oscillator. It is also called as free running oscillator. Why oscillator? Because we are not applying any triggering. Without applying any external trigger, it generates the output oscillations of square wave. So hence it is also called as square wave oscillator also. So these are the different names. Bistable multivibrator is called flip-flop, binary, Eccles-Jordan method. Monostable multivibrator is called as one-shot, or even it is named as pulse generator because it generates a single pulse. Coming to astable multivibrator, as it generates continuous oscillations of square wave, it is also named as free running oscillator or square wave generator. So this all is a brief introduction about the multivibrators and its classification. What is stable state, what is quasi-stable state, and based on stable states, quasi-stable states, we classified the multivibrators. And in multivibrators, we also have seen here what is the type of coupling we are using. In bistable, it has two stable state, 0 quasi-stable state, number of triggerings required are 2, and here the coupling, based on coupling also we can define. Coming to in bistable multivibrator, both the couplings are resistors. In monostable, we have one stable state, one quasi state, one number of triggering is required, and one is coupling element is resistor and the other coupling element is capacitor. Astable multivibrator, 0 stable states, 2 quasi stable states, and 0 triggerings are required. And coming to coupling elements, both the coupling elements we are using are capacitors. This is a brief overview of the multivibrators classification. Now we will move to the one of the multivibrator circuit and how it produces the output waveform. So coming to Astable multivibrator, I'm taking here Astable multivibrator. Astable multivibrator, as I said, it is also called as free running oscillator or square wave generator. Why Astable multivibrator is named as free running oscillator means without applying any external triggering, it itself generates the output waveform of square wave oscillations. As we are not applying any external triggering or any external input, it produces the output of square wave, hence it is an oscillator, free running oscillator. And why it is called square wave oscillator? Because the output waveform, if you see here, output is a square wave. So it is also named as square wave oscillator. As we know, a stable multivibrator has 0 stable states, 2 quasi-stable states, and 0 triggering is required. So this is basic information we require in order to understand the working principle of a stable multivibrator along with its waveforms. It has 0 number of stable states and 2 quasi-stable states and 0 trigger is required. So as I said, we use 2 transistors. Let me name one transistor as Q1 and other transistor as Q2. Cross-coupled connection is there. So here is this is a base terminal, this is the emitter terminal, this is the collector terminal of transistor Q1, this is the base terminal, emitter terminal and collector terminal of transistor Q2. So here the output of first transistor, the collector terminal of first transistor is coupled through the coupling element C2 to the base of second transistor input. This is a coupling path. And the output of second transistor, usually we collect it collector terminal. The collector terminal of second transistor is coupled to base of first transistor through another coupling element C1. So here if you see, both the coupling elements are capacitors. So as I said, in a stable multivibrator, we use capacitive coupling. So the type of coupling we are using in a stable multivibrator is capacitive coupling. One is C2 and one is the C1. So this is a cross-coupled connection in this multivibrator. So collector terminal of first transistor is connected from power supply through a resistor RC1, let us assume, and collector terminal of second transistor is connected from the supply through a resistor RC2. So let us try to study the working principle of a stable multivibrator. So as we know, a stable multivibrator, we need not to apply any external triggering. If you see the circuit, other than supply voltage VCC, we are not applying anywhere the external input. So that's the reason the triggering used is 0. So before understanding the working principle of a stable multivibrator, let us assume, so here are the 4 waveforms I have drawn here. We are collecting 2 output waveforms. One is at collector terminal of transistor 2, which is named as VC2, and one we are drawing the waveform of base terminal of transistor Q2, which is VB2, and one we are taking the output at collector terminal of first transistor, which is VC1, and one waveform we are taking it base terminal of first transistor, which is VB1. So totally we are drawing here 4 waveforms to understand the working principle of a stable multivibrator very clearly. So first, second transistor waveforms are VC2 and VB2. First transistor waveforms are VC1 and VB1. So this is a circuit diagram and these are the 4 waveforms in order to study the working principle, how it changes the states continuously without applying any external triggering. Let us try to study the working principle of this. So initially at t is equal to 0, this is an instant I am taking at t is equal to 0. Before t is equal to 0, let me assume transistor Q2 is off. So I am writing before t is equal to 0, Q2 is off. So at a time one transistor is off and other transistor is on. So at t is equal to, before t is equal to 0, Q2 is off, Q1 is on. So initially for t is equal to 0 minus, t is equal to 0 minus means less than t is equal to 0. I am assuming my transistor Q2 is off and transistor Q1 is on. So out of the 2 transistors, one transistor is on and other transistor is off. So basically transistor operation, if we can understand, for a non-transistor, if we assume the output I am collecting at this point, as this is on, it is closed path. If I just wanted to collect the output at this point, it is 0.3 volts. VCE saturation we will get. So for a non-transistor, Q1, the output voltage VC1 is 0.3. So if you see here VC1 waveform, for t less than 0, it is 0.3 volts. And for the same, as this is on transistor, minimum base voltage. For a non-transistor, minimum base voltage required is 0.7 volts. So if you see here, VB1 waveform also for t is equal to less than 0, 0.7. So this is a first transistor is on, for which output is 0.3 volts. And the minimum base voltage required to turn on your transistor is 0.7. So these two we are drawing. Similarly, Q2 was off. For an off transistor, this path is open circuit. As this is nothing is there here, this is open switch. So your supply is directly connected to collector terminal of second transistor. If you collect your output, it is VCC is directly connected here. So output VC2 is VCC. For t less than 0, VC2 waveform is VCC, and as this is off, base voltage is somewhere negative. Base voltage is somewhere negative. So VB2 waveform starts from some negative voltage. So for t less than 0 instant, these are the 4 voltages. VC1 is 0.3, VB1 is 0.7, VC2 is VCC, and VB2 is, as this is off transistor, some negative voltage. So for t less than 0 instant, I have drawn the same. VC1 is 0.3, VB1 is 0.7, VC2 is VCC, and VB2 is some negative voltage. So for t less than 0, this is an instant. So now let us try to understand, as this is on transistor, so this capacitor C2 finds the charging path. This is a charging path of the capacitor. This capacitor finds the charging path from the power supply through the resistor R. This is the charging path of the on transistor. Through the resistor R2, this capacitor finds charging path. So as this capacitor C2 finds the charging path, as this is a cross-coupled connection, because of this cross-coupled connection, in this charging path, when your capacitor C2 is charging towards VCC, that particular point is connected with base terminal of Q2. So your capacitor starts charging in this manner. It can charge maximum of VCC. Maximum it can go up to VCC, but it is not required up to VCC. Whenever the voltage, as this is charging path is increasing, whenever it gets, till then it was negative. Whenever it gets minimum voltage of 0.7 in this path, the transistor Q2 changes its state. It goes to on state. So when your capacitor is charging towards VCC, whenever it gets a voltage of 0.7, that is more than enough to turn on your Q2. So now Q2 has changed its state on. So as Q2 is on, this is closed path for a closed transistor. Now the collector voltage goes to 0.3. So the BB2 waveform is 0.7. Collector voltage, all of a sudden it changes its state to negative voltage, which is 0.3 volts. Then, so here the collector voltage is, earlier it was VCC, now it has dropped to 0.3. VCC, if I assume it as 12 volts, 12 volts minus this 0.3. 12 minus 0.3 is 11.7 volts. So this 11.7 volts is connected to base of transistor Q1 through this coupling path. Till that time this was at 0.7. So 0.7 minus this 11.7, it goes to minus 11 volts. Minus 11 is negative potential, which makes your transistor Q2 is off. So till that time it was at 0.7. The voltage drop is minus 11 volts. So it is dropped with minus 11 volts. So all of a sudden your VB1 waveform changes its voltage level from 0.7 to minus 11. So with this minus 11 volts, your transistor Q1 has changed its state from on to off. So if you clearly understand, initially I assumed Q2 was off and Q1 was on. Without applying any external trigger, after some duration of time, Q2 has changed its state from off to on and Q1 has changed its state from on to off. So as we know, it has two quasi-states. So quasi-state means without applying any trigger, it has to change its state by itself. So we did not apply any external trigger here. It has changed its state off to on to off. Now the same criteria, because one quasi-stable state we have explained here and another quasi-state. So we need to see. So as now here the second transistor is on. So with this on transistor, the same criteria here, this capacitor finds charging path. So this is a charging path. In this charging path, this capacitor is coupled to this transistor 1. So whenever this transistor Q1 gets enough voltage, this changes its state from off to on. Similarly, when this has changed its state from off to on, automatically this goes to off. So if you clearly try to understand, initially we assumed off, on. Without applying any external trigger, the state has changed on, off. And after some time again it has changed, this has changed on, this has changed to off. Twice the multivibrator is changing its state. So hence we have two quasi-stable state, and this is all explanation is without applying any external trigger, continuously the outputs are changing here. Output is changing, output is continuously changing. Hence it generates square wave oscillations. So here the title Astable multivibrator is also called as square wave generator, as it produces square wave oscillations. And these two waveforms we are taking here, VB2, VB1 waveforms. Because of capacitor charging path we need to understand, we are drawing VB2 waveform and VB1 waveform. So Astable multivibrator, without applying any external triggering, it has changed its state from one state to another state, hence the name square wave oscillator. Thank you.